And welcome to Otten Math. In this edition of Otten Math, we're going to graph systems of linear inequalities. Or at least we're going to talk about graphing systems of linear inequalities. All right, so that's chapter 3.3 for us, but if you're not following along, there's no chapter needed. So some terms and definitions. A solution of a system of inequalities is an ordered pair that is a solution of each inequality in the graph of the system. So in the system of linear inequalities, we can have no solutions. Potentially, we could have just one solution, or we could have an infinite number of solutions for the linear inequality. All right, the graph of a system of inequalities is a graph of all the solutions of a system. So let me just give you an example before we move on. So what we mean when we're talking about graphing systems of inequalities, let's just say that I have two equations for two lines. I have my xy coordinate plane, and I'm going to draw one line, and solution is going to be everything below this line. So let me shade that in red. So I got my solution, everything below this line. And then let's say I have another line, and this line will be in blue. And this graph looks something like this. And then the solution for the this particular inequality is everything also below the line. Oh, I got it in red again. It's going to be everything below the line. We'll get into this in just a second in more detail, but I just wanted to give you a picture first of what I'm talking about. And so the solution is going to be that set of solutions or ordered pairs that represents solutions for both of the inequalities, both for the inequality that's represented by the red and the inequality that's represented for the blue. Right? So that's a graph of the system of inequalities, represents all the solutions to the system, and I have an infinite number of ordered pairs in the solution in the blue and red area. Okay, so let's move on and talk about graphing the systems a little more specifically. So you're going to be given two linear inequalities. So the linear inequality looks something like the two givens above. I have x and y greater than or equal to, less than or equal to. And remember, and we'll talk about this in just a second, if it's less than or equal to, the line that's being represented is going to be solid because the line is included as part of the solution. And if it doesn't have an equal sign, then the line does not represent part of the solution, so you make it a dashed line. All right, so let's see what we got here. Now let's take on a problem. Graphing a system with two linear inequalities, so I'm up at the top of the page, and I'm given two linear inequalities, 2x plus 5y is greater than negative 5, and x plus 3y is less than 3. So the first step is to graph each of the inequalities. And what I like to do is I like to rewrite the two inequalities in slope-intercept form because it's much easier to deal with. You're given, once you rewrite it in slope-intercept form, so y is equal to mx plus b. Once you write it in that form, you have the slope and you have the y-intercept. It's very simple to graph. So what we're going to do is we are going to rewrite these two equations in slope-intercept form. So in the first equation, I need to subtract 2x from both sides and then divide by 5. So step one is 5y is greater than negative 2x minus 5. And then I'm going to divide both sides by 5, and I end up with y is greater than negative 2/5 x minus 5 over 5, or minus 1. So I'm going to write that here in this area that I've provided for us. Y is greater than negative 2/5 x minus 1. And then I'm going to erase the work that I did here and work on the second equation. Okay, so my second equation, I have x plus 3y is less than 3. So I will subtract x from both sides. So I have 3y is less than negative x plus 3. I divide both sides by 3, and I get y is less than negative 1/3 x plus 1. And I'm going to take that inequality, which is really an inequality in slope-intercept form. Y is greater than negative 1/3 x plus 1. All right, so now I have the two inequalities in slope-intercept form, except instead of an equal sign, I have an inequality sign. Okay, so The second step now is going to be, or part 2 of step 1 is to draw the boundary line. And the boundary line is equal to the line that we're given, assuming that instead of the inequality greater than, and I made a mistake here, didn't I? I'm sure you all caught that. In my class, I'd give you a starburst for catching it. But good thing I caught it here before I finish this video. So y, and I do this all the time, and I'm sure you do too. That's why we always double check our work when we take tests. So y is less than negative 1/3 x plus 1, not greater than. So the first thing I want to do is draw the boundary line. And as I mentioned before, if it's less than or equal to, then the line representing the boundary line is going to be solid. If it's less than or greater than, then it's going to be dashed because the line is not part of the solution. So in this case, we want to pretend that the inequality sign now is equals, and we want to draw that boundary line. So we have y is equal to negative 2/5 x minus 1. So let's go ahead and draw y is equal to negative 2/5 x, and I believe I said minus 1. But let's just double check. Negative 2/5 x minus 1. Okay, so y is equal to negative 2/5 x minus 1. I know the y-intercept is going to be negative 1 here. My slope is going to be negative 2/5, so I'm down and to the right. So let's plot a couple points. So I'm going to go over 5 and then up to 1, 2, 3, 4, 5. So that's my change in my y. And then up to, so negative 1 up to, I have a point here, negative 5, 1. And then I'm going to go from this point here, I'm going to go over 5 and down to 1, 2, 3, 4, 5, down 2. And here is the other point. So let's graph this and let's draw a straight line. We're going to draw the straight line in blue. And actually, we know it's going to be dashed, so I can't draw that straight line. So let's draw our straight line as best we can using this cursor. And I think we're doing a good job here. It's a dashed line again because this line is not part of the solution. All right, now we're going to change this equal sign and to what it actually is an inequality. And that's going to be y is greater than negative 2/5 x minus 1. So let's go ahead and change that equal sign to y is greater than. And I'm kind of running ahead of my notes here that I've given to you, but we're just going to go ahead and solve this whole thing at once, and then we'll go back over the notes. So y is going to be greater than negative 2/5 x minus 1. So now we want to test a point. I'd love to test 0, 0 to see if it's part of the solution. So if I were to test a point, I'd say 0 for y is greater than negative 2/5 times 0, which is going to end up being 0, minus 1. So 0 is greater than negative 1. Yes, that is a solution. So I'm going to shade in 0, 0, and everything else that's on that side of the dotted line that represents the solution. So here we go. Shade this all in because we know that 0, 0 is a solution. So everything on this side of the dashed line is going to be a solution. Okay, so let's take on our second inequality. Y is less than negative 1/3 x plus 1. Y is less than negative 1/3 x plus 1, and let's do that in red. Y is less than negative 1/3 x plus 1, which we're going to change to y is equal to negative 1/3 x plus 1. And we're going to go ahead and we're going to graph that equality using a dashed line. And we know that the y-intercept is 1. We have a negative slope. So we're going to go over 3 and up 1. 1, 2, 3, up 1. And we're going to draw a point here. We got a point here, and then we're going to go down 1 and then over 3. 1, 2, 3. And it looks something like this. So I'm guessing we've got a dashed line. It looks like it's going to cross somewhere in the second quadrant, but let's check it out. Okay, so now I'm going to test a point 0. Let's test 0, 0 again because that works just as well. We test a point 0, 0, and we'll see if that works. If I have 0 is less than negative 1/3 x, which is 0 plus 1, That's correct. So 0 is going to be part of the solution. It's going to be below the line in this case. So I'm going to have a little sandwich here, and let's draw this in red. I mean, bear with me as my computer is a little slow right now. So everything else below this line works. And then we need to shade in really the portion in between this line here, which is above the dashed blue line. So our solution is going to be this area, this wedge in here. It looks like this. Okay, so let's go back through the steps just so that we're clear on what is going on. We talked about what a solution means. We had two inequalities. We changed them into y is equal to mx plus b form, but with the inequality symbol. And then we made them equal to that value in order to graph the boundary line, making it dashed or solid depending on what the inequality was. If it was greater than or less than, we dashed. If it's greater than or equal to or less than or equal to, then it would be a solid line. Then we graphed both of the lines. We tested a point for each of the inequalities to make sure that that point was true. And then we shaded in the respective areas and found the common shaded area, and that's going to be our solution. Okay, so let's go back through the notes. So step number 2 is identify the region of solutions for each inequality separately, which we did. So remember in this Jackson Pollock painting, we've graphed the blue area that represents the solution above the blue line, and then graphed the red area below the red line that represents part of the solution for the second equation. Okay. We tested the point, which we did. We tested 0, 0. We completed the same process for the second equation. And we identified the area that is common to both inequalities, and that represented our solution. Okay, that's it for Aughton Math. Come back and join us for some practice problems in Chapter 3.3, Graphing Systems of Linear Inequalities.